right? I thought there'd be data. Is anyone out there?
Welcome back. So what happens if we try to make T star better and say maybe T double star, because that's an unbiased estimator, and we can again condition on that sufficient statistic or even a different one. Well, let me look at that one first. All right, so that's what that would look like. That double expectation thing. Remember when we showed, let me use a different color. Remember when we showed that the expected value of a random is what we showed, right? Yeah. So here we can say that this guy is just the expected value of t given s, which is t star. So we're not changing anything. And using that same rule, like this iterative expectation thing that we proved, that was pretty easy to prove, it didn't depend on anything like any kind of special relationship between x and y. They could even be dependent and it's still true, or they can be independent. So for that matter, I could put any like S2 here, still going to get this result. So it's a really good idea, and I'm really glad someone else, I should have said that, because it seems like, why can't you just make it better and better and better until you can't? Well, you can't. Okay, so did that make sense? All right. No, yeah.
Can I ask a quick question about that?
Mm-hmm.
So if you replace S with a different sufficient statistic, yeah, like this S2 you're putting in here,
So
wouldn't you get the expected value of t given?
so S, and if you t given and S2, those will be different. Is that what you're asking?
Yeah, and so that doesn't necessarily mean that t double, at least it's different.
Yeah, different. Okay, so I have a new class of statistics that I think you're going to hate. Everyone always does, because the definition is so bizarre and unmotivated. But hopefully today I can motivate us. And this is a class of statistics known as complete statistics. Hang on. Okay, so for these two lines here, I was assuming we were using the original t.
Mm-hmm.
Are you saying now this is an unbiased estimator, so we should put it in here?
Yeah, I guess.
Yeah, so that is going to be exactly this with s equals s2. And so then t double star would be t star. So they may be different, but they're not necessarily different. So you either have the same. Oh, but the variance of that. So the variance will not be going down. It will stay exactly the same, because t star and t double star would be exactly the same. So if you just started with a t and did this conditioning, you'll get something unbiased for tau, and then did this one, you'll have something unbiased for tau. And as it stands here, these can be relative variance. But if you take this guy and put it in here, then your t double star will have the exact same variance. And in fact, there's no point in doing that. That's that iterative sort of thing. Does that make sense?
I think I would maybe like to talk about it some more, but I can ask after class.
Okay. I know you were trying to avoid complete statistics. No, you don't know what you're in for. Okay, so suppose I have x1 through xn IID, or maybe not IID, although for us, it will always be IID. So I can write like this is kind of a new notation. I started using it last time. You know, this is my short way of saying this vector valued random variable has the distribution kind of corresponding to this joint PDF. So PDF, f of x vector semicolon theta. And so it's entirely possible that these can be IID, but this allows for a little more generality. Okay, I can't even say so today. I'm a little tired and stressed out for some reason, but I'm not going to say what that is. I'm not supposed to bring that into the classroom. So here's the definition. A statistic S is complete for the model or the parameter. We sort of have the same language problems or language ambiguities we have with sufficient statistics. So a statistic S is complete for the model G. So I'm just going to write any function G such that the expected value G of S is 0 for all theta in the parameter space. We must have that G of S is 0 with probability 1. So you can certainly think of random functions whose expected value is 0, and that doesn't mean that the function itself is 0. But if that is a function of a complete statistic, I wanted to start with a couple of examples of showing that some things are complete. This is generally hard, and then you're going to say, don't we have a factorization criterion? And I'm going to say, kind of, yeah, we have one. It's a little more restrictive than our factorization criterion for sufficiency, but it will get us a complete statistic in a lot of cases. And in the example, hopefully I will clarify what all of this means. Okay, so let's do it. Let's do like a uniform 0 theta. So x1 through xn, IID, uniform 0 theta. And I think we showed, no, we haven't. The maximum is sufficient for estimating theta here. Oh yeah, we did. We did that with our factorization criteria. We know that the statistic S defined as the maximum is sufficient for theta, or this model. And so the question here is it also complete? Function G such that the expected value of G of the maximum is 0 for all theta in the parameter space. If you can't find one, that doesn't mean you're good to go. But if you can find one such that, let me just do it. So let's try to show it. Suppose is such that the expected value of G of S, which is the expected value of G, suppose that this is 0 for all theta in the parameter space. And the parameter space here is all theta is greater than 0. So let's write out what that expectation is. The expected value of G of the maximum, I am going to just put G of X in front of the max PDF. And integrate over the whole space. In this case, the whole space is, well, I'll write it as minus infinity to infinity, but the PDF for the maximum is going to cut us off. This is going to be the integral from 0 to theta G of X. By the way, the factorization thing coming up will not work in all cases. So this is not a waste of time just to convince you that the other thing is great. This may be your only way to show something is complete. And then the PDF here is not that you have to know this by heart, but x to the n minus 1, and and then we get a dx. Okay, so I am going to suppose that this is 0, and I want to be able to conclude that g is 0. So I'm going to do that here by taking the derivative on both sides with respect to theta. And, oh, no, I can't do that yet.
Question.
Yeah.
So wait, so that line, so equals.
Oh, this was here.
Okay, cool. That's what I thought. I just
Yeah.
wanted to make sure.
Yeah, sorry. I'm a little lopsided here. Before everything, this thing is 0 if and only if. This implies that the integral from of g of x, x to the n minus 1 dx has to be 0. Pull out the n, that's a sample size. Pull out the 1 over theta to the n, that's not going to make it 0, even if theta was allowed to be 0. So this must be 0. And now I'm going to take the derivative on both sides with respect to theta. And on the left side, I'm taking a derivative of an integral with respect to theta. One is going to give me g of theta, theta to the n minus 1 equals 0. And then all of these lines greater than 0. For all theta greater than 0 and for all theta greater than 0. So if this is 0, then that forces g of theta to be 0, right? Because this can't be 0 for this parameter space. So this forces g of theta to equal 0 for all theta greater than 0. And we can use any argument we want. This tells me that g of x equals 0 for all x greater than 0. I mean, it's just another variable. And so this tells me that g of the sufficient statistic, which is going to be 0 because the g is identically 0. And I do get to with probability 1 because nothing about the lines above said anything about what g has to be if the argument is negative. So we could have a g that is crazy and then I need to make up some kind of, actually, no, I mean, the idea would be to make up some kind of function of the maximum whose expected value is 0. But we now know that means that the function is identically 0. So I can't come up with a g whose expected value is going to be 0. But I will have examples coming up later today where we show some things are not complete by exhibiting a function that is has expected value 0 or 0. So please, you can always just answer this question by saying, I take the statistic to be vector valued, and I'm going to take it to be x1 through xn. But let's find an interesting sufficient statistic. So I'm going to use the factorization criterion that we had, our joint PDF, because they're IID, it's a product 1 to n of the individual PDFs, which is a product as I goes from 1 to n of e to the minus lambda, lambda to the xi over xi factorial, and an indicator, which is important. I mean, it's important anytime we have a theorem that relies on us being able to factor things into x parts and theta parts. That's when you have to be careful about the indicators. Okay, so this is n lambda, lambda to the sum of the xi over the product as I goes from 1 to n, product of indicators. We want to write it as, we want to pull out the pure x, that's fine. You're going to take this as your h of x function, or yeah, I mean, there's multiple h of x functions we can take, but what we're looking for is something like h of x, which doesn't depend on the parameter, and then g of s of x and theta, where s is some function of the data that we're looking for. So let me not this factorization criterion, or in this case, lambda. So there's no, but from this, my g of s of x and theta is equal to e to the minus n, I keep saying theta, it's lambda here, is equal to e to the sum of the x. So then you look in there and you say, how does the data present itself? What kind of statistic do I need from the hallway to evaluate this? You need the sum of the x's. So this implies that s, which is this little function, this function little s of the capital X's, which is the sum of the goes from 1 to n, is, today we're doing completeness. So let's quickly show it's complete. So now show S is complete for this model. It may not be complete if I start with different distributions. So I need to grab any function g such that the expected value of g of S is 0. So g such that the expected value of g of S, is 0 for all parameters in the parameter space. In this case, that's all lambda greater than 0 because that's the parameter space for the Poisson distribution. Can't find one. I mean, we're not going to actually look for one. This is more of a, it's going to be really hard to exhibit one because this statistic is complete and that is going to force this g function to be identically 0. But if you are trying to just imagine you can start with one in order to such a function, then you have a complete statistic because you cannot exhibit a g such that this expectation is 0 for all parameters and the g is not 0. So if you can't find a function g, you're okay for completeness. The thing is, if you can find a function g that satisfies this, we have to be able to show that g of s is 0 with probability 1. Okay, so I'm going to use the fact that S has a Poisson distribution with parameters n lambda, and I'm going to write out this expected value of g of S. This is going to be the sum as S goes from 0 to infinity, g of little s, and then this Poisson PDF, e to the minus n lambda to the s over s factorial. And I'm going to suppose or set it equal to 0. I suppose this is 0 for all lambda greater than 0. It's possible that it's 0 for a particular lambda and that the function itself is not 0. But for completeness, you want to assume it's 0 for all parameters in the parameter space. So this one is a little bit tricky. I'm going to pull this out, and that's not going to affect it. And what I am left with is that the sum as s goes from 0 to infinity of g of s n to the s over s factorial and my lambda to the s. I'm going to write it this way. I'm going to say g of s over s factorial. And then n lambda to the s, I guess. So I'm assuming this is 0 for all lambda greater than 0. So what we have here is a power series in lambda. We've got an a1 of s lambda to the 1 plus an a2 of s lambda to the 2, etc., equaling 0 for all lambda greater than 0. It's a pretty ugly coefficient, but that's what we have. And so I don't know how you feel about power series being identically 0. So let's think polynomials. This is an infinite polynomial. It's not exactly going to cut it, but suppose this was a polynomial of degree n, then it has at most n zeros. There's at most n values of lambda that you can plug in to make this 0. And so you can definitely plug in some lambdas that may make this 0, and that doesn't make the 0. But if this is going to be all lambda, and if you're thinking polynomial, it can only be 0 for up to n of the lambdas. This is going to force this to be identically 0. So this I'm going to write implies, and then I'll write parenthetically kind of what I just said. The 0 for all lambda greater than 0 implies that all of these coefficients are 0. And it's the for all lambda that's doing that. So one more time, if that's problematic, cut this off quadratic like this. It could have at most 2 zeros. And yet I'm saying it's 0 for all lambdas greater than 0. That can't happen. It's not clear from that what happened in infinite series, because maybe you can have an infinite number of zeros. But in fact, you can only have a countable number of zeros. And that is to avoid here. So I claim this is 0 for all lambda greater than 0. The coefficients are 0. I'm trying to say S with a TH after it. The S coefficient is this. This must be 0. And the S factorial can 0, even 0 factorial is 1. Also, it's in a denominator. The n to the s can't be 0, like n to the s could be 1 if s was 1. But this forces g of s to be 0 for this function could be crazy between integers, but this implies that the g of the capital S, now this is a Poisson random variable which only takes on non-negative integer values, does not imply that g is identically 0. Like that g of x is 0 for all x. And in this case, we can have something even weirder than my example with the uniform. So imagine a function of s that is just 0 on the integers to only take on those values, 0, 1, 2 on up. There's probability 0 of s being something between 0 and 1. So that's me 0. You just need it to be 0 where. Any questions? Let's just get to the easier way. But before that, maybe why do we care? Yeah, question.
So up there when we had that power series is equal to 0, what we're really saying is for all lambda, that series.
It's definitely hand wavy in here. Why do we care? So do you agree with me that this is like the worst thing we've defined? It's just so weird and not intuitive. But this is why we care. Why do we care? So if S is complete out of theta, from some distribution that depends on theta, and from that we make a statistic. And so S is going to, and so if S is complete, this implies there is only one function of S that can be unbiased for tau of theta. And you might wonder why you care about that, but let's prove this statement. It's going to be pretty quick. So the proof of this statement is, okay, suppose there are two. Suppose there can only be one. So value of G1 of S is tau of theta. We have one function that's unbiased for tau of theta, and the expected value of G2 of S is also tau of theta. So this means that you can get 0 from tau of theta minus tau of theta which is the expected value of G1 minus the expected value of G2, which is the expected value of the difference G1 of S. But if S is complete and this expected value is 0, the G1 minus G2 is the new function G. And so this implies that G1 of S minus G2 of S is 0 with probability 1, because this thing inside here is what I want to call my new G of S, and S is complete. This is since S is complete. So we've got that these functions are the same, which is what I was claiming, but I still need to convince you why you care about this. But this proves the claim, at least the same with probability 1. This proves the claim that if you have a complete statistic and you're looking for functions of that are unbiased for tau of theta, you can only find one. And why do you care about that? This is going to be a picture that's going to make no sense if you look at it later. So suppose this is your estimator, this is my estimator. By that I mean like on, and you have some kind of function G2 of some S2, and someone else has a G3 of S3, someone else has a G4 of S2, yeah, I mean 2, someone else has a G5 of S2, and we have a whole bunch of estimators, and they're all unbiased for tau. And we're trying to figure out whose is the best. We're trying to go to the umvu. By completeness, if S2 is complete, just as an example, then all of these guys are equal. So if you throw out as many possible estimators of tau of theta that you want, and you're trying to find the best, I can sort of rule out or clump together a whole bunch of them to be looking at of any complete statistic. All of those would be the same. So again, if S1 was also complete, the words did. Does that make sense? We like completeness because it helps us narrow things down. All right. So, okay, so I know you're thinking, no, I don't. I always say that. Is there not a factorization criterion that's going to help us out? Because right now we're guessing at a complete statistic and then going through a horrible procedure and imagining infinite series. And, it's not fun, nor is finding one fun. So the question that I know you're thinking is, do we have something like a factorization criterion for completeness? A factorization criterion sort of thing for completeness. Yes. So I have two definitions for you. And from each definition, I'm going to pull out a complete and sufficient statistic. So suppose joint PDF, I'm being very sloppy. You start with a distribution, some IID things maybe, or maybe not IID, maybe an X1 through Xn with some joint distribution that depends on theta. But suppose your joint PDF can be factored. Wait a minute. I'm still looking at that darn sticky note. I don't know when this class ends. Suppose it can be factored as follows. So I'm going to take my joint PDF as a function of all the x's and theta, and I'm going to assume that I can factor it into some function a of theta, some function b of the data, kind of trying to separate things, and then e to some function c of theta times some function d of x, where things make sense. So by that, I mean, you definitely can't have your a of theta identically 0, because then your PDF is 0 and it doesn't integrate to 1. Like, oh, I need b of x to be non-zero. Otherwise, it's not a PDF. So things that make sense in order for this to be a PDF, just the really obvious things. So maybe it would have been better if I wrote this. You can't have A and B 0, and you actually can't have C of theta to be a constant. Those are the rules. Okay, I'm defining something. Then we say that the distribution is a, darn it. This is a definition where theta is one-dimensional. I'm going to give a definition for a higher dimensional theta. So then we say, here's what we're defining. We say that the family is a one-parameter exponential family distribution. This is a one-parameter exponential family distribution. So that's what I'm trying to define. One parameter exponential family distribution. So I claim, we're not going to get to show it this time, but I will probably get to some examples. I claim that the statistic S defined to be the D in this factorization evaluated at the random X's is complete efficient. Which I will try to convince you of. Find a k-parameter exponential family, but I think instead of doing that, I want to do an example of this. So by the way, sufficiency is very easy to see here because if you can factor your joint PDF like this, the G, and then you go in there and you say, how do the X's appear? They appear in this function D of X. So from the factorization criterion, it should be pretty clear that this thing I defined is sufficient. Completeness is a little bit of work. But let's get an example because you definitely don't need e's or exponentials in your problems. You know, you can always put in e's of logs, right, and make things work. So as an example, but this is one of the less simple ones, IID Bernoulli's with parameter p. So I want to find a complete and sufficient statistic. So I'm going to try this one parameter exponential family. First of all, we have only one parameter, so that's good. I'm going to write out the joint PDF, which you get from multiplying the individuals. And this is p to the sum of the x's, 1 minus p to n minus the sum of the x's, and a product of indicators. Again, very important whenever you are using some kind of theorem that says you can separate things. The parameter was in the indicator, you're never going to be able to truly separate this into part, theta part, x part. So there's a hint that anything that is, if the theta is in here, you really can't get it out. Okay, so what? So I think I'll make this part of my pure x stuff. And then in here, the x's. So this I can write as, let me write the whole thing. I've got this product of indicators, which is going to be the A of X part in the exponential family factorization, 1 minus P to the N, which is pure parameter, and over 1 minus P to the sum of the X's. So this is, you know what, I wrote this in this order and I didn't even get it right. This is the A of theta, in this case P. This is the B of X. And now we're going to just make this look like the E of a C of theta D of X. And so to do that, I'm just going to write this one more time. Make it in the right order. I'm going to write this as E. to the log of all of that stuff. And then I'm going to bring the exponent down in front of the log. There's the b of x. This is the c, and this is the d of x. So by one parameter exponential family, that's a thing you say. You would even say that on a prelim. The statistic S, which is the sum as I goes from 1 to n of the capital Xi, is complete and sufficient for this distribution, for this model, for this parameter. Easy for a lot of cases until you don't have an exponential family. Questions?
So presumably then showing something as a one parameter exponential family will be easier than showing this complete.
Oh yeah.
Okay.
It's just write out a joint PDF and then try to factor it into a pure X part, pure parameter part, and an E with a pure X part, pure parameter part. Yeah, way easier. I mean, the second example I did, we didn't even really completely finish because we had to say some things about series, and those were the easy ones. Other questions? Okay, so I think the last thing I can get in some other class, ghosting this class. That's not what ghosting means. Okay, so here's a definition. If theta is k dimensional, for us it's usually two dimensional if it's not one dimensional. So that's a k, hard to read. And the joint PDF can be written as f of the vector x and theta. If we can write this as some a of theta, some b of x, and then an e of the sum as I goes from 1 to k of a ci of theta di of x. Notice I did not use a theta I anywhere. So there's no like separating the individual components of the thetas out. Then we say that the distribution is a k-parameter exponential family. Similar claim, the statistic S defined as the components of the D's, D1, D2 of X out through D. I'm writing bigger and bigger because I'm trying to make things look random, but if everything is big, that doesn't work. This is I'm going to write is complete and sufficient. So I can say it's either a complete and sufficient vector or those k things are a collection of complete and sufficient statistics. So for fun, go home and try you're home. Go somewhere else and try this normal distribution and show that you can factor it so that you can get down to the sum of the xi squareds and the sum of the xi, which we already saw were sufficient for estimation here. But by exponential family, we will also have completeness. Thank you. So go away.